Hello, I would like to offer a greater amount of intuition about electrical power, electrical resistance, and also things like real batteries and voltage changes across electronic devices. So what I have here is a circuit diagram representation of a voltage source, that is a battery, let's call it. And notice that the voltage source can be set to whatever we like. So right now it's at 6 volts. I'll set it to 12 volts. And then let's let the electrical resistance be, well, again, anything we like. And for now, we're setting it to 12 ohms, but let's go ahead and change that to 24 ohms. Okay. So notice that we can, with a single resistor here. Now notice the symbol for resistor. The circuit symbol for resistor is kind of that zigzag, sometimes called like a heartbeat shape. But this is a pretty standard schema for an electrical resistor. And we also have a switch. And the switch is off right now, so that means the circuit it's an open circuit. We can close the switch, and then that's going to be the circuit is on. So let's go ahead and see what the result is. Okay, so notice the conventional current, labeled I, as an arrow. The charge moves off the positive terminal of the battery through the circuit and then returns to the negative terminal of the battery. And in fact, the current goes through the battery itself. So notice that the electric current is 0.5 amperes. How do we get that? If you saw one of my earlier videos, you noted that electrical current is voltage divided by resistance. So delta V divided by R equals I. So 12 volts divided by 24 ohms should give 0.5 amperes. Now, one thing we should think about calculating is the electric power. Since there's only a single resistor, we can calculate the electric power delivered by the battery by using the equation I times delta V. That is current times voltage. So since the current is 0.5 amperes and the voltage is 12 volts, if we multiply those, we have 6 watts. That's the electric power in this resistor. Notice that volts is joules per coulomb. Notice that amperes is coulombs per second. Thus we get the units of joules per second, which is energy per time, and that's also the units of power, which is watts. Okay, let's open the switch, and now let's make a change. Let's change this to a resistance of 12 ohms. So 12 volts divided by 12 ohms, that should be 1 ampere. Let's think about what the power is. Well, the power is going to be 12 volts times 1 ampere. That's going to be 12 watts. Now there's another way to calculate electric resistance here, and that is the equation I squared times R. So if power equals I times delta V from Ohm's law is I times R. So the equation I squared R is electric power. So I squared is 1 times 1, that's 1 squared, times R, the resistance of 12 ohms, gives 12 watts. Finally, the last equation that we could also calculate with to get electric power is going to be voltage squared divided by divided by resistance. Okay, so that's because if power is equal to I times delta V, I is the same thing as delta V over R from Ohm's law. So you get the equation delta V squared over R. Well, voltage is 12 volts. If we square that, that's 144. Divide by the resistance of 12 ohms, you still get 12 watts. So those are all viable ways to get the electric power. Notice that if we keep the resistance the same, but we increase the voltage, let's say, to 16 volts, notice that 16 divided by 12, we should get we should get a current, and now in this case the current is way too much because this resistance can only handle 20 watts. So let's go ahead and open the switch. Let's go ahead and make it a little less. Okay, notice now we have a pretty large current because it's 14 volts divided by 12 ohms. That's 1.17 amperes. Notice the power is 16.33 watts. Again, that's either I times delta V, or it's I squared times R, or it's delta V squared over R. Okay, so this is how electric power works. What I would like to show now is the intuition behind voltage changes across electronic devices. In fact, let's use a 12-volt battery again, and this time let's use the PhET simulation, so phet.colorado.edu, and the Circuit Construction Kit DC Virtual Lab, and let's use this as a voltmeter. So notice when we use this voltmeter, a voltmeter is going to measure voltage across the device. Notice that even when the switch is open, when we measure across a battery, notice that the voltage is exactly 12.0 volts. Notice also if we switch the direction of the polarity of the prongs, it'll measure negative 12 volts. That's because there's sort of a polarity direction to the battery. This is the positive terminal, this is the negative terminal of the battery. Now notice if we take the same battery and we switch its polarity in place, notice the voltage switches to negative 12 volts. And again, the battery itself is rated as positive 12 volts. A voltage source is rated at its positive value. So let's reverse the battery direction again. So we have the polarity we expect. Now notice, when we try to measure across a voltage across the light bulb, notice that the voltage right now is 0. That's because no charge is flowing, and then furthermore, notice that both the left-hand end of the black prong of the voltmeter and the right-hand red prong of the voltmeter are both in line with the left-hand terminal of the battery. That is because no charge is moving. All points here are at the same electric potential. That is, there's no change in the potential energy. But notice, if we keep this black prong upstream and we move this red prong over to piece of wire which is connected to the positive terminal of the battery, we should get 12.0 volts. So all this portion of the line is at a potential, electric potential, that's voltage, of 12.0 volts, and then this entire part of the line from the negative terminal all the way to where the switch is open, all the way up to here, is at an electric potential of 0 volts. Remember, voltage is sort of relative. You are free to choose where the 0 value of voltage is. But by convention, we typically choose 0 volts to be associated with the negative terminals of batteries. Let's go ahead now instead and put the switch into the closed position. Notice that electric current is now present. That is, charge is moving. And let's go ahead and now measure the voltage across the battery. The voltage across the battery should hopefully still be 12 volts. And that is what we find. But now let us measure the voltage across the light bulb. So the voltage across the light bulb is now 12 volts. And let's think about why that is. Because all the electric potential energy is becoming dissipated energy per unit charge in the light bulb. Furthermore, we know that negative charges are coming off the negative terminal of the battery, but then electric power is being dissipated in the light bulb, and that the other side of the light bulb is now at a lower electric potential, that is, at a lower voltage than the upstream side. So you could imagine one side is at positive 12 volts, that's over here, and the other side over here is at negative 12 volts. In fact, it's probably better if we label in terms of conventional current. So think about positive charges coming off the positive terminal of the battery, this upstream side all the way up to here, so this entire side on the right hand side is all at 12 volts electric potential, but then the left hand side here, all these pieces of wire are at 0 volts. Now when we cross the battery, we immediately jump from 0 to 12 volts. But then again, that's just a source of electric potential energy. So I hope that makes sense. Wouldn't matter where in the piece of wire, as long as it's on the positive side of the battery, that there's going to be a voltage difference of positive 12 volts. But notice that if the black is way over here, we get the same reading. But also notice that if we put the red and the black next to each other on the same piece of wire, downstream of the bulb, all connected to the negative terminal of the battery, there's 0 voltage difference. That's because this entire line is the same electric potential. The reason current keeps running through it is because of the inertia of the charges, but there is no change in the electric potential energy per unit charge, that is the voltage, through a connected piece of wire. Okay, hope that makes sense. Finally, in this video, I would like to show how electrical power renders itself when we have real batteries. So we really know that batteries themselves have a little bit of internal resistance. That's usually labeled lowercase r. And we also know that real resistors have load resistance. So by the way, this load resistance is a lot of times the sum of all the resistances out there in the larger circuit. So let's assume the battery resistance is 1 ohm and the load resistance is 6 ohms for now. Notice that the entire resistance of the circuit will just be the sum of these two resistances, that's 7 ohms. 12 volts divided by 7 ohms via Ohm's law should be 1.71 amperes. Notice if the internal resistance of the battery was 2 ohms, notice that the current goes down, but now the math is a little bit easier. So 2 plus 6 is 8, 12 divided by 8 is 1.5 amperes. Notice when we go from point A over here to point B, notice that from point A to the battery, we jump from 0 to the battery's EMF. Now, by the way, EMF is an archaic term. In the 1800s, EMF meant electromotive force, but I will never use that phrase again. I will call it EMF because an EMF is a voltage. It's an electric potential energy per charge. It's definitely not a force. So the EMF allows us to go from 0 volts to 12 volts. This is the graph that's meant to show what is true downstream of this battery. When we cross the resistor, which is meant to represent the internal resistance of the battery, notice there's a slight decrease in the voltage. The voltage decreases by I times R, current times that small amount of resistance. And in this case, the decrease of that voltage should be 1.5 amperes times 2 ohms, because I times little r is voltage drop across the battery. And the voltage drop across the battery in this case should be 3 volts, because 2 times 1.5, 2 ohms times 1.5 amperes, 3 volts. Then there's 10 volts remaining. Sorry, I said that wrong. There's 9 volts remaining, there we go, to spend in the rest of the circuit. Let's assume these wires are resistance free. So only once we get past point C do we hit this resistor, and we go from point C to point D, the voltage goes from 9 volts down to 0 volts. So this part of the line is all at 0 volts, and it does not jump up past point A until we get back to the battery. So I hope this makes sense. And I want to thank everyone for their attention. Please share this video if you like it. Subscribe to this channel. Please smash that like button. And I will see you in the next video. Thank you for your attention.